So that, of course, is Arieh Isereles, who, along with Richard Friend and myself, organized this. So I'm very thankful to the co-organizers. I'm also thankful. You can tell this is a math course because I don't have 11 logos here with different funding agencies and institutes I belong to. But I am want to thank the Simons Foundation that made this collaboration. For those of you who were here yesterday, you realize this is an unusual collaboration. There's 10 of us PIs really spanning the gamut from very experimental physics to very pure harmonic analysis, geometric measure theory. I'm the computational guy in the middle, and that's sort of the focus of today. It's going to be on computational techniques. We started yesterday, Marcel gave a nice introduction to landscape theory for the physicists. I'm going to give the same talk, only it's going to be sort of from the point of view of a mathematician. I see many fresh faces, so I won't worry about repeating it. So what's the story about localization of eigenfunctions? Probably some people don't know what that word means, localization in this context. It's the following phenomena. So it applies to more general PDEs than Schrödinger, but let's talk about the Schrödinger equation. So we're talking about the Schrödinger Eigen Value equation. Again, you can tell I'm a mathematician because the eigenvalue is called lambda, not E. And I'll switch between what I would use as the most common notation and just H for the Hamiltonian, mostly used in quantum mechanics. So let's take the case where the potential V is 0, or a constant, and let's put periodic boundary conditions. Then the first eigenvalue is the constant, and the other eigenvalues are sines and cosines, plane waves. Like this one is the 57th eigenvalue. If you have a real potential, some smooth function or something like that, then these change a little bit. Instead of getting something constant, you get something that wiggles a little bit, and you get still sinusoidal looking things for the higher eigenfunctions. The key point about these is they extend all the way in space to the ends of the domain. If we were on the whole plane, they would extend out to infinity, basically plane waves. In quantum mechanics, indicating that the particle can travel anywhere, the electron whose state function is psi. But now let's talk about localization. That comes in when you add disorder. So here's my potential. It's a completely random potential. I did it by taking the square, cutting it into 80 by 80 subsquares and putting a random number on each one. And now we compute the eigenvalues, the first and the 57th, and you get that. So you get these little tiny spikes. I guess I don't have to keep walking if I have this pointer. You get these little spikes. So at least to the eye, it looks like the support of the eigenfunctions is very, very tiny. That's localization. And just to start asking the questions we want to ask, this is very important in applications. Well, how do we know whether we're going to get spikes? If we are, how do we know where they're going to show up? Why did it pop up over here rather than somewhere else for the fundamental? What about the thickness of the spikes and the shape and the eigenvalues and so forth? People want to get a handle on that, and that's what localization theory is a new tool to do. Now, why do you care about crazy potentials like random numbers? Well, here's a real-life application from one of our collaborators, Jim Speck's lab. So that's a LED semiconductor device, indium gallium nitride, aluminum gallium nitride semiconductor device. And these little green dots that you're seeing, or dots in lots of colors, are individual atoms. This whole piece is about half a micron long, and there's 60 million atoms in it. And using this wonderful machine, this atomic probe tomography machine, they're able to map the position of every atom and color them by what kind of what kind of atom it is. So we know the exact nature of this sample, and if you look at it, well, grosso modo, there's some big green, some big red, then some sort of periodic stuff. But if you look up closely, there's lots and lots of disorder in it. And that's absolutely crucial to its functioning as a device. Sometimes that's a good thing, sometimes it's a bad thing, but it's the thing you want to use and control and eventually optimize. And so that's an application where getting a handle on the eigenfunctions in disorder is very important. Okay, why do you get spikes? Well, there's one kind of spike that everybody who studied quantum mechanics, even in the first book, knows, and this is what comes to everybody's mind, is square well with finite walls. So here I'm doing a 1D Schrödinger equation, and this is my potential V, It's 0 for a little piece of the domain, and then some value nu for the rest of the domain. Then it's a very easy calculation that you could all do with a pencil and paper to figure out what the eigenfunction is. And so the fundamental eigenfunction will be, you can write it in terms of cosines and exponentials. And it'll be confined to this well, more or less, but it'll dribble out, tunnel out, a little bit with an exponentially decaying tail. And the higher the walls are, the faster it'll exponentially decay outside. So if you have such a structure, you expect a localization for the low eigenvalues. The eigenvalue is lower in energy level than the height of the walls. Okay, but of course we don't have such a thing. How could we extend this to more general potentials? Well, the most important tool in this whole business goes back to Shmuel Edmond, 1982, who showed how you could get decay for a much more general set of potentials as long as they have sort of well-like structures, wells that go down with high walls around them. And so he introduced something called the Adron distance. Specifically, he considered regular potentials, so fairly smooth, not these piecewise constants we're looking at. And he did it on all of Rn, n dimensions but no boundaries. And technically speaking, he viewed the Schrödinger operator as a closed unbounded operator acting on L2 and Rn. And now I'm going to read the second part twice, once for the mathematicians, once for the physicists. For the mathematicians, what's the Adron distance? It's a metric on the domain that says the distance between 2 points is the shortest geodesic distance measured in the Riemannian metric, which is conformally flat, with the conformal factor being the square root of the amount by which the potential exceeds the eigenvalue, positive part. If that didn't rock your boat for you, let me give an example. Suppose you're trying to measure the distance, you're on some surface or something like that, and you're trying to measure the distance between 2 points. So a way to define it, not a practical measurement, is to walk from one to the other on every possible path you could think of, and count the number of steps on each path and take the lowest that you get. Now let's make it a little more complicated. Let's say we don't only want to measure the distance, but we want to weight it by something like the temperature. When it's very hot, we count it as more distance. So we multiply by the amount the temperature exceeds 20 degrees centigrade or something like that. And then add that up and take the minimum. That idea is the Adron distance, a weighted distance. And the weight is the amount by which the potential exceeds the eigenvalue level lambda. And you cut it off to 0 when the potential doesn't exceed lambda. So it's a degenerate distance. There's no distance between 2 points in the well. They're at 0 distance from each other. Okay, so with that definition, Adron proved the following rigorous theorem, somewhat simplified here. If you take an eigenvalue of the Hamiltonian with eigenfunction C, and you make the following assumption. You have a regular potential V, which is above lambda for all but a finite region, all but a bounded region, which stays above lambda. Then there's something that's true for every number less than 1. Let's pretend it was also true for 1, because it's true for 0.99999. So let's take alpha as 1. And it says the integral of e to the 1, e to the Adron distance from x to a fixed point like the origin. So you take e to the distance to the origin in this Adron distance, square it, but first you multiply it by the eigenfunction c, and the result is integrable. You get a finite integral. And you're integrating all over Rn something that's growing exponentially. How could that be? Well, the only way is if that exponential increase is canceled by an exponential decrease of c. So what this is a technical mathematical way to say c is decaying exponentially. And there's a theorem that says if you have a potential like this, then the eigenfunctions associated with the eigenvalue lambda decays exponentially. Okay, so can we use that to analyze? Oh, by the way, feel completely free to interrupt and ask questions, especially if there's terminology or something like that. Any questions? Okay, so can we use that kind of reasoning to analyze what this random piecewise constant potential? Well, the answer is no, it doesn't apply directly. And I'm going to give you an extreme example that makes it completely clear it doesn't apply at all in this example. My random potential, instead of taking a random number between 0 and 1, here I took the number either 0 or 4. White is 0, black is 4. And I assigned it randomly, and I weighted it 70% zeros, 40%, 30% 4s. Okay, anyone who knows percolation theory knows this percolates, which means that there's a path connecting almost every white point to every other white point. In fact, that's a connected set that I put in pink there. Almost all the white stuff is in one big connected set. So what does that mean? That means that there's no wells surrounded by walls. The wells have depth 0 and the walls are height 4, but there's no white enclosed in black walls. So you can't, the Eigen distance between any two white points is 0. There's no exponential decay from that theorem, even if that theorem didn't require smooth potentials and so forth. Okay, well, so we need something new. And I'm very lucky that two of my collaborators, Marcel and Svetlana, invented something new in 2012, which is called the landscape function. So this is a simple idea with big implications, and exactly what's going on underneath the simple covers is not so clear. So you take an elliptic operator, can be much more general than a Schrödinger operator. Basically think any operator that the maximum principle holds for. You need to do more than that. It might have rough coefficients, the domain might be complex, the boundary conditions might be tricky. But in such a one, you define the landscape function by just solving HU equals 1. Minus Laplace U plus V times U equals 1. Simple PDE, simplest possible right-hand side, other than 0. And of course, boundary conditions, whatever you're doing, Dirichlet, or I'm always doing periodic, but it doesn't matter. So if you solve that, then they prove the following error estimate. Any normalized eigenfunction psi, normalized means that we'll set the L infinity norm to 1, satisfies the bound that psi is greater than lambda times, is bounded above by lambda times u, an absolute value. So another way to say this is if you divide both sides by lambda, it says if you take an eigenfunction psi and you divide it by its eigenvalue, so you give it a height proportional to 1 over its eigenvalue, so the fundamental is the highest, the next one's a little lower, the next one's a little lower, that will always be less than this function u. So let's see that in a concrete case, and it'll make it clearer.
Does it mean that u is non-negative on this?
Yes, because h satisfies the maximum principle and 1 is positive. So here's a potential, for example. There's a 1D example where it's easy to see. I pick 64 random numbers as the potential. Then for that potential, I solve minus u double prime plus vu is equal to 1, hu is equal to 1, and you get this function u, which is, by the way, is called the landscape function. So we have this landscape function u. Then on the same graph, I plot the first 4 eigenfunctions, and I scale them so their height is 1 over lambda. And you see all 4 eigenfunctions sit nicely underneath the green curve. And that's always the case. That's what the theorem says, not only for 4 eigenvalues, but for all eigenvalues. Okay, so if you go back to Marcel and Svetlana's original paper, this was presented as an explanation of why eigenfunctions localize. If there's a place where u...
This BE is lambda?
Yes, I didn't change all my slides to prove I was a mathematician. Some of my best friends are physicists. So the reasoning went, well, if you have one of these random potentials, then the landscape function has these peaks and valleys, as you can see here. It tends to be big when the potential is small, and small when the potential is big, although it's more complicated than that. So if you go to a place where it has a peak and then valleys to the side of it, that's going to force the eigenfunction down by this bound, so it probably goes to 0 and localizes. Now that last step was somewhat unclear, but that was sort of the reasoning. We got a better perspective on this, I think we all agree, a few years later. This was work with also with those two and also with David Jerison and David and I, which we did the following computation. It's a computation that you can't do in 2 minutes, but you can do in 20 minutes, and you'll get it right. If you take the Schrödinger Hamiltonian minus Laplacian plus v and conjugate it by multiplication by u. So that means multiply a function by u, apply that operator to it, and then divide by u. And then do the calculation, and you'll find that splits using the fact that u is the landscape function. You'll find that splits as this divergence form elliptic operator. Well, it's only divergence form with a weight in front, with a density, and a new potential. And the new potential, lo and behold, is just 1 over u, 1 over the landscape function. So all of a sudden, 1 over the landscape function is a potential. Not the original potential, a new, smoother potential. That's the new viewpoint, that the key guy is the effective potential w is 1 over u. And there's also this sort of interesting looking elliptic operator L. And
there's a missing minus sign, minus L.
Sorry, it should be minus. Actually, I'd like to put the minus inside the definition of L. But so it's L plus W, but it should be a minus over here where I have the red. And now whenever you conjugate an operator, the new operator has the same eigenvalues. So doing this didn't change the eigenvalues. So this new operator, L plus W, has the same eigenvalues as before, but now it has a much nicer potential W. That's the idea. In addition, the Eigen Vectors are related, the Eigenfunctions are related to each other by a simple relationship. The Eigenfunctions for L plus W are just the original Eigenfunctions over U. So here's those points I made. W is revealed to be an effective potential, and its characteristics are it's smoother than the real potential. It's confining in the sense of having wells and walls, even when V is not. And you can see that in this picture. This is the effective potential, 1 over U, for the for this Bernoulli potential there that didn't have any wells. That one had no wells. It wasn't confining. But the effective potential has lots of wells where it is confining. The colored things are basically the walls, and where it dips down and white is the wells. You can see it also here, these deep lakes of blue surrounded by green.
L is not self-adjoint.
L is, you're the guy who knows it. L is self-adjoint in a different inner product, U squared. You're always telling me you multiply two symmetric by a positive definite, it's still self-adjoint.
Same norm.
That's right, it's self-adjoint in the U inner product. In the U squared weighted inner product. You're absolutely right. Christoph?
What happens when you iterate this?
A lot of things. So somebody had a poster today on iterating this. It'll be clearer towards the end. And maybe not completely clear. And finally, and here was the key tool in the paper that we wrote together, the math paper we wrote together, was okay, so W has wells and walls, so you can do an Eigen distance argument for that, and it's not vacuous. This has a meaningful Eigen distance. And so that's our approach, to use the Eigen distance associated to W instead of V. And you have to have, of course, you have to know how to run it. There we go. You have to have a movie, right? So this is the level sets of W, the effective potential in the 3D case, and what you see is these deep purple wells surrounded by green. That's saying in 3D we have the same thing, an effective well and wall structure, so we can do an Eigen distance argument. Okay, this is what we're able to prove with that. If you have such a basin of W confined by walls or crests which remain above some eigenvalue lambda, then we can show that the eigenfunction for the L plus W equation decays across those lines, and we do prove this using the effective Eigen distance. And then the original eigenfunction is just that eigenfunction divided by W, or multiplied times U, and since W is a positive guy, this makes it even smaller. So this proves exponential decay as long as the W has wells and walls. And here's the precise math way to write it out, actually simplified a little bit. It's a little bit of a mess, but what it says is that if you have an area where the effective potential is above where the effective potential is above the eigenvalue lambda, then, well, it basically says then in such a region you will have exponential decay from the value of the eigenfunction in the area where it's below lambda. So let me show it to you numerically. So actually this implies more than we would have thought. This doesn't say only that there's exponential decay at one level, but whenever the walls go back above lambda, there's exponential decay. So what you see here is a picture and the domain. The black lines are the places where the walls are going above the eigenvalue lambda, and the color there, the red-yellow color there, is showing you the eigenfunction, which is indeed confined in one of the wells. Okay, we'd seen that picture many times before in one way or another. It's now sort of proven by that theorem, but more interestingly, if you take the log of this, then you get this picture. So these are plotting the same function, but on the right it's on a logarithmic scale. You see it's order 1 here in the middle, and then it goes down to like order 1/10 and 1/100th here, which is the exponential decay you saw. But you see it's more or less a solid color in each of the well-like regions, and then as it crosses into the next well-like regions, it drops down in color. So it decays exponentially, and actually I'm showing you here 13 orders of magnitude of decay that's implied at this. So one of these localized eigenfunctions doesn't look like a spike in 0. It looks like a spike where it gets down to 1/100th, and then another drop where it gets down to 1,000, and then another. It keeps dropping exponentially every time it crosses high walls. I don't think that was known before. Okay, so that's a quick introduction to landscape theory. And now the question I want to ask, I want to put on my numerical analyst cap here and ask whether this is sort of a numerical method. Is this a way to compute spectra? Christoph.
Can you just say again, where does the randomness come in? It sort of sounded like you only need the ridges.
So to apply this theorem, you only need the ridges. You need to have a potential that has wells and walls.
So if it's a periodic potential, that still applies?
If it's a periodic potential, so you have a periodic potential, let's say it bounces between 0 and 1. You apply the landscape function, you'll find it's nearly constant, and you won't have a structure of wells and walls. However, if you took a square well, which is very non-random, and you apply get the effective potential, it'll still have a well, and so there'll still be exponential decay out of a square well. Okay, so the question is, can we sort of use this as a numerical approach to compute spectra? So it's almost the opposite of what I've done up till now in this talk. I've been using numerical analysis to compute the spectra, finite elements and Krylov-Shur solvers and things like that, and to learn about the landscape theory. And then we find that they're sort of very correlated. So now can we use the landscape theory to learn about the spectra? Okay, so here's a game. I had the fun of playing this game, and the contestant was Jim Simons, the Billionaire Foundation head. And the question was, if here's your potential, 256 random numbers. And the question is, we solved the Schrödinger eigenvalue problem, where does the fundamental eigenvalue pop up?
Did Simons get the answer right?
Not only did he not get the answer right, he declined to play, I have to say. But he passed it on to his panel, which is of course what he does, and they played and they lost. Thank God. Okay, so is there any of our Schrödinger experts who want to guess where in this potential landscape? And collaborators cannot play, since this is about the 11th time you've seen me do this. Anyone want to take a guess? Okay, the wise move is not so easy. But the idea is it's going to somehow appear in the deep wells. But you look at this potential, what's a deep well? Well, it goes down pretty far here, but it's awfully thin. goes down quite far here, that's fatter. Here's a, how do you decide? There's no linear measurement that'll tell you. So here's how we do it. We use the landscape theory. So we compute the landscape equation. So we solve minus Laplacian u plus vu is equal to 1. That's easy to do, one finite element solve. And this is our effective potential. I take the reciprocal, and this is our effective potential. I should remember to use this dot. Okay, now we have now there are clearly wells and walls. There are a bunch of wells, and this is clearly the deepest one. So that's our answer. This is where it should. Let's see.
Yeah, that one's
This one is a little lower. I can't see it.
the one on the far left.
You think the one on the left is lower. Well, I'll find out because I did the computation. So, there we are. You're absolutely right. The lowest is this one. I thought it was coming out to be this one, and I was very confused. But no, it is this one. The lowest, the second lowest, almost tied with the third lowest, and the fourth lowest. Sorry, I should use this pointer. So that's our prediction where the first 4 eigenvalues will show up. We also make a prediction how fat the eigenvalues will be. We go up to the height of this minimum till it's doubled and take the sublevel set of that set. So in other words, we do this. For each one, I want to double the height. The 2, using a factor of 2 is, of course, a choice, depending on how conservatively you want to estimate the fatness of it. So this is my prediction, that we'll have those 4 as the eigenfunctions, and they'll be roughly as fat as the green boxes indicate. And then for this simple one-dimensional example, I compute the exact eigenfunctions and compare. And those are the exact eigenfunctions, number 1, 2, 3, and 4, in exactly the order we expected, exactly at the points you expected, and roughly with the thickness you expected. So it shows that there's a lot of information, at least in this simple example, in the landscape function about where the eigenvalues are going to show up. Okay, now you know how to play the game. There's another round, bonus round. Where would the eigenvalues going to appear for this potential? So we have it.
Yeah, there.
Tell me where. Okay, that's where it did for the last potential. And you're absolutely, well, it's reasonable to do that because this potential is the same as the last one with one difference. I multiplied it by a factor of 64, so it has a difference. Before it only went up to 4, now it goes up to 256. So unless you were paying attention to the amplitude before, you should make the same choice you made before. But you should have been paying attention to the amplitude. So now we do it, we get the effective potential. It looks totally different. It's much closer to the true potential. It cares about the thin wells much more, and the winner is the longer. Right? It's the deepest well is this one. So I mark them, 1, 2, 3, 4. So they occur in totally different places than before. Lee.
I have a question. So in physics, you have this h bar factor in the Laplacian.
Yes.
So I assume you scale the physical units out.
Yeah, that's another sign I'm not
Right.
a physicist.
Okay, but in the correct scaling, and if you scale everything out to as many ones as possible, what's the actual size of the potential?
Well, so this is 256 m over h bar squared, which depends on what units you use, but if you use meters and seconds, it's 10 to the some large number. Claude probably knows. Yeah, no, I have to take the mass of an electron and so forth.
Okay.
So these are, the way I've done this, a potential of roughly order 1 is a moderate sized potential. Much bigger than 1 is going to have very sharp localization. Much smaller than 1 will start to delocalize. Yeah, scaling is a big issue in this business. Okay, so here's where we predict the eigenvalues will appear. And I put on the green bars, you can barely see them, they're so thin in this case. So that's what we're predicting for the eigenmodes, 1, 2, 3, 4, and we compute them, and they're spot on. Also for this case. So that shows you how nonlinear this process is. Same potential, different amplitude, totally different results. And now we do it in 2D. So they go back to that 80 by 80 Bernoulli potential, compute the landscape function, take the reciprocal for the effective potential. You get this thing we saw before with blue ocean surrounded by green walls. You find the local minimum. There's number 1, 2, 3, and 4. You take a sub-level set around each one of them. You get those shapes, and that gives us our eigenfunction prediction. Looks like that. And then you compute the real eigenfunctions, which now gets a little bit expensive. And you get those 4 eigenfunctions. And now I overlaid our prediction with them, and they're spot on again. Now, I won't claim that this never fails. That's not true.
Can you compute this eigenfunction locally?
Yeah, so that's one of the things that I'm hoping will come up in this workshop. So once we know that these are localized, we could probably just cut the domain off here and compute it there, or we could do a very adapted mesh, highly adapted here. Of course, you have to know where it's localized, so maybe use this theory to get it started. There's lots of issues there, and Kaibo's poster is about this approach. So that's a very interesting question. Okay, so now I'm going to do a 2D case that fails, not badly, but you'll see what goes on. It's an 80 by 80 potential, but this time random numbers between 0 and 20, I believe. You compute the effective potential, it looks very different, but you still see that there are blue wells surrounded by green walls and red walls. So you mark the deepest local minimum, 1, 2, and then 3 and 4. There are 2 minimum that virtually coincide and their sub-level sets merge. Not quite sure what to do with that. Maybe we should only call that 1 minimum. And then we have the 5th one is shown there. And then I look at the real life. Well, the first 4 eigenfunctions happen in those places, but not quite in the right order. 1 went to 1, the fundamental was right, but 2 matched with 4. And 3 and 4, which merge, match with 2, and 5 with 3. Now this is not very terrible, because the eigenvalues are very close together. You should think of the following example. Suppose we're trying to compute 2 eigenvalues, and one of them is 1.5, and the other one is 1.5001. And the 1.5 has this eigenfunction, and the 1.5001 has this eigenfunction. We compute an eigenfunction of 1.5 with this eigenfunction exactly. Somehow we get it correct of 13 decimal places. And then we compute one with eigenvalue 1.49999 and this eigenfunction. So that's a great match also. However, when I say what's the first eigenfunction, that would be this one, and it's a terrible match for the first eigenfunction of the real problem, which is this. So you obviously have to allow some permuting of eigenfunctions, or else you're going to have failures that aren't really failures. Exactly how to do this when you might also be missing an eigenfunction, or it's not exactly clear. So I don't regard this as a real failure, but it shows the subtleties of what could come up. Okay, that was eigenvalues. Now let's talk, eigenfunction positions and thicknesses. Now let's talk about, if you want to know more about the eigenfunction than just how thick it is, the structure. So for this we use the Agman distance in a big way. So we have our theorem that says that the eigenfunction is not really asymptotic to, but is bounded by an exponential e to the Agman distance of x from the center of the eigenfunction. And we know how to compute the center of the eigenfunction. You compute the minimums of the effective potential. We saw that's really accurate. So then we could compute the Agman distance from that point. So now how difficult is this to compute these Agman distances? Well, it turns out that's actually quite easy. If you have a point x0, you know your weight function, w minus lambda plus. You can compute the distance in that weighted distance metric to any point by solving an Eikonal equation. And Eikonal equation, the solution of that goes by fast marching methods. It was exactly what Jamie Sethian worked on. So there's nice software to do that. It's rather easy to take one point and compute the Agman distances to that point from every other point. So then that leads us to the following algorithm. We take our potential and compute the landscape function and its reciprocal, the effective potential. Then we estimate the center of the ith eigenfunction by the location of the ith minimum of w. and we estimate the eigenfunction itself by the value of that minimum. We'll get to that point a little bit later. Then we compute the Eigman distance for that for W and that estimated eigenvalue from the point x0 for every point x. And then we estimate the eigenfunction itself by this bound here, x e to the minus Eigman distance. So that seems very crude, but it's surprisingly good. So in this picture on the left-hand side is the exact eigenfunction, fundamental eigenfunction for that 80 by 80 Bernoulli potential. And the right-hand side is what you get if you use this Eigman distance approximation that only involves solving the landscape function. Now look carefully at these. They're not exactly the same. The one on the right is a tiny bit fatter, and some of the details have gone away a little bit. Actually, I even have an idea why it is a tiny bit fatter. But it's certainly a pretty good initial guess to get without solving any eigenvalue problems. If we look at a logarithmic scale, it's even more impressive to me. This is the exact eigenvalue, 34 orders of magnitude, but these are not actually orders of magnitude. This is base E logarithms, so 34 powers of E. And here's the Eigman distance approximation of it, and you see it's qualitatively very similar. We get the magnitudes right way down to what it's like 10 orders of magnitude or 34 powers of E down. So by using this Eigman distance, we really predict the eigenfunction relatively accurately over the whole domain. Okay, so let's give this a little bit more of a torture test. Let's look at a few more eigenfunctions. That's the one we just saw. That's the second eigenfunction, and what we get by the Eigman distance estimate from it. And you can see we've lost some detail, but we basically got it right. And again, we basically got it right on a logarithmic scale as well. Third eigenfunction, a similar story. Fourth eigenfunction, a similar story. Fifth eigenfunction, by the way, we have periodicity, that's why the eigenfunction picks up on the other end. Similar story. Sixth eigenfunction is a little different. This is an eigenfunction that has a significant negative part. Basically, it's not the fundamental eigenvalue of the basin it lives in, it's the second mode of the basin it lives in. The Eigman distance is e to the minus something, so it's always positive. The Eigman distance is giving me an envelope, it's not picking up the oscillation, and that's what you see here. So it missed that completely. It did get the location right and some aspects of the shape right. Seventh eigenfunction is like the ones we had seen previously for the most part. There's a little bit of a negative part in here that got screwed up in here. Then this one's a complete failure. Well, it's that kind of failure we saw before. The eigenfunction that we computed with the Eigman distance is the wrong one. It's not the one that corresponds to this one. So the eighth eigenfunction is trying to be matched to something that's the wrong match. The ninth eigenfunction is okay. And then the 10th eigenfunction was the one that the 8th was trying to match, and vice versa. So this is a case where the order of the local minimum is slightly different than the order of the eigenvalues. They're probably very close to each other. So that gives you some feeling about the good and the bad of this. Now, we have a good initial guess. So any numerical analyst would say, okay, well, I have a good initial guess, now let me use an iteration to improve it. Jinchao's already suggested one way to do that. If we were solving a nonlinear equation, we all knew what we'd do. If we have a good initial guess, use Newton's method and it converges very fast. The equivalent for eigenvalue problems is to use Rayleigh quotient iteration. So here's the Rayleigh quotient iteration algorithm. You start with an eigenvector and an eigenvalue. And now you want to get a better approximation to the eigenvector and the eigenvalue. To improve the eigenvector, what you do is use the eigenvalue you have as a shift to shift the spectrum of the operator, take h minus lambda, shift it so that it's closest to 0 at lambda, and then do one solve of not an eigenvalue problem, just a source problem, using the old eigenvalue on the right-hand side. So in other words, you take your eigenvalue and you hit it with h minus lambda inverse. That will magnify the component in the direction of the eigenvalue closest to lambda much more than the other ones. That's called the shifted inverse power method. And then, if you want to get a new eigenvalue, so you can continue this, you take the Rayleigh quotient, which means you take the inner product of C, H, and C divided by the L to norm of C squared. So this is Rayleigh quotient iteration, and its nature is two things. It always converges to an eigenpair. It's fast as hell once you get close. So once you get close to something, it converges fast as hell. And the technical definition of fast as hell is that the error at one step is the cube of the error at the previous step. So if it was 0.01, then all of a sudden it's 10 to the minus 6. Club.
Don't we call that perturbation theory in physics, in quantum mechanics or physicists?
No, come on, perturbation. The answer to your question is no. Moving on. So I did a little experimentation with this. We haven't worked this out carefully yet to a robust algorithm. So in this picture, in the bottom right-hand corner is the exact eigenvalue. That's ground truth. That's what we're trying to compute. On the top left corner is the eigendistance estimate. That's our initial guess. We already saw it. It looks quite a bit like the exact eigenfunction, but it's a little too fat, and some of the details are blurred. Then we do one iteration, because we're quite close already. We do one iteration of Rayleigh quotient iteration, and we get something that, in my eyes, I can't distinguish between these two: first iteration and exact eigenfunction. And second iteration also changes. If you actually print out the errors, you get errors like a small fraction of a percent, and then the next error is like 6 digits correctly. So it's a very fast approximation. So this may be one way to go forward with the landscape theory, to compute initial guesses using eigendistance, and then do something like Rayleigh quotient iteration and combine it with the kind of things that Jin Chao was suggesting that uses adaptivity and localization. Okay, and let me finish up by talking about predicting eigenvalues rather than eigenvectors. So to show you that that the effective potential or the landscape function has information about eigenvalues in it, let me first just do a lower bound. There's a trivial lower bound for eigenvalues. You take the original Hamiltonian, you can write that as the L2 norm of the gradient squared plus the inner product of VC and C. And I apologize, this is another place where I'm a mathematician. I write my inner products with commas and parentheses. You write your inner products with bras and cats. Now what you do is you throw away the grad C squared because it's positive, so that's why it's a lower bound. You get VCC, and then you say, well, this is bigger than if you take V to be its minimum value, its infimum value, so you replace V by its minimum value. And now you have a Rayleigh quotient. The left-hand side divided by the W squared from the right-hand side is a Rayleigh quotient, which is the eigenvalue, and that's greater than inf of V. So what you proved out of this is that every eigenvalue is greater than the infimum of the potential. Trivial.
W is psi. It's a misprint.
W is psi. That's right. That's not because I'm a mathematician. That's just because I'm tired. Okay, but now let's do this again using the effective potential. So minus Laplacian plus VC is U L plus W psi over U. That's the conjugacy relationship. Break that into two pieces, U L of C over U plus W C over WC. The over U's cancel. And then I remember what L was, and I multiply this by C, taking psi is equal to U phi, and what you get, the U squares exactly work out. That brings in the U squared that I needed to make this work out, and I get U squared L psi over U. That's positive, because U squared times L is a divergence form operator. That I can throw away. And then the other term is WCC. So this other calculation shows you that WCC is the lower bound for the eigenvalue, and of course that's bounded below by the infimum of W. So instead of using the infimum of the true potential, you can use the infimum of the effective potential. by a slightly more complicated argument. Now look at this picture. The true potential is shown in gray. Its infimum is virtually 0. It happens right here, because if you choose 64 random numbers, one of them is going to be near 0. But the effective potential is the blue thing. That doesn't have nearly as deep peaks. There, the infimum effective potential is where my pointer is now. That's a really reasonable bound. And then the red line is the true fundamental eigenvalue level. And you see the W bound is reasonable, the V bound is meaningless. Okay, now I want to go beyond a lower bound and give you a heuristic for getting values of eigenvalues. And pay attention to this argument because it's very hokey. And it's certainly not a proof, and you can decide whether it holds any water or not. The reasoning behind this argument is if you take a local eigenvalue that's supported in some well D, like this red one here is supported in roughly this interval here, then it looks more or less like a bump. Well, it seems to be more or less like a bump. And it looks more or less like the U above it, which is another bump that's a little bit bigger. Of course, U is not a bump globally, but it's a bump on that well. Okay, now the eigenvalue is the Rayleigh quotient, the integral of CHC divided by the integral of C squared. And since the eigenfunction is essentially 0 outside of D, we can compute the integrals on D. On D, C looks like a multiple of U, and a multiple doesn't matter here, that cancels out, so I can replace C by U and get the Rayleigh quotient of U computed on D. But now U is the landscape function, HU equals 1, so the top simplifies to the integral of U over the integral of U squared. And now we say, well, U is sort of like a bump, so it sort of looks like this picture, which is clearly a lie. It doesn't look very much like that picture, but let's pretend it does look like that picture. It's a paraboloid that's going down to 0 on its well. Then you could compute integral of U over U squared. And the amazing thing is that the integral turns out to be sort of independent of what the paraboloid is, or more precisely, the integral turns out exactly to be 1 plus the number of dimensions over 4, so in 2D, 1.5, or in 1D, 1.25, divided by the maximum of the paraboloid U, or another way to say that is multiplied by the minimum of 1 over U. So that's how we get this heuristic that the eigenvalue should be about 1 plus the dimension over 4 times the global minimum of the effective potential, and all the other eigenvalues that correspond to other minimums to the corresponding minimum of the effective potential. So in other words, the depths of the local minimums tell you what the eigenvalues are, multiplied by a fudge factor, which is exactly 1 plus d over 4 by this hokey argument. That's where we are. Let's try it. So here I took the 80 by 80 uniform potential that had values between 0 and 20. I computed 100 eigenvalues for some random realization. I computed the corresponding local minimum and I plotted them. You see they have a fairly same shape, and the claim is that they're in ratio of 1 plus d over 4, where now d is 2, 1.5. So I compute the ratio, and I plot it. This is a plot from 0 out to 2. Here's 1.5, and the ratios stay very close to 1.5 for 100 eigenvalues. Here's the same thing with the Bernoulli potential. It has a different shape, but it's still shadowed by the minimum. It's not quite as good a match for 1.5. The first 20 eigenvalues are very close to 1.5, except 2 that deviate to maybe 1.6 or 1.7 for one of them. And then it slowly floats up towards like 1.7. What?
Experimental error.
Yep, I'm showing you the warts and all. Here was another potential that had correlation. That one turns out to be even better. Then this is one I did because one of my collaborators said, well, this is because everything's on a nice uniform square mesh. Turns out not to be true. I put it on the worst mesh I could think of. Totally unstructured triangular mesh with anisotropic long thin elements. And then I plotted on the x-axis the mins, W min, on the y-axis the eigenvalues, and so if they're in the ratio of 1.5, they should be on the line through the origin with slope 1.5, and there it is. Notice I didn't take a line and fit this data. I took the line with exact slope 1.5, and not any line with 1.5, the one through the origin, and the line right up on it. My favorite picture in this business is one I just did recently that shows 1D, 2D, and finally with my postdoc Wei Wang we computed 3D. He computed 3D. And what I did is I did 30 or 32 different random realizations of the potential in 1D in blue, and 2D in red, and 3D in green. And for them I printed out the first eigenvalue, the 10th eigenvalue, and the 25th eigenvalue, all 32 different values of it that I got. What you see here is the eigenvalue would vary from below 1 to nearly 3. So the fundamental eigenvalue will vary by a factor of 3 depending on what random numbers you choose. But the W min adjusts for that, so it ends up right on the line with slope 1.25 in all cases. And so the work is, it's very predictive. So there's something called the Journal Club for Condensed Matter.
You have also first tens and 25th.
What?
It's all of first tens and 25th and 3D as well.
First, 10th, and 25th eigenvalues.
You know,
32 realizations of each. So like these red squares are the 25th eigenvalue, 32 realizations using in 2D. Even you're impressed.
yeah.
So there's something I learned called the Journal Club for Condensed Matter Physics, a monthly selection of interesting papers by distinguished correspondents. And they chose our paper on this subject. Here's the citation for their paper to be suggested in August by a guy named Carlo Benneker. I checked, it's the first time that this journal has been selected for a paper in there. In fact, the first time any science journal has been selected there. It's usually either Nature Science or else a condensed matter journal. And this is what Carlo Benneker wrote. To appreciate how astonishing, he was referring to a figure similar to the one I just showed you. To appreciate how astonishing this is, imagine someone telling you of a new method to find the eigenvalues of a large random matrix. I invert the matrix, sum the rows to obtain a column vector, then search for the local minimum and its reciprocal elements. This sounds like a crazy method, but figure 2 show it works for localized eigenstates. So it is a surprising, if you look at it, and without this landscape theory behind it. Okay, and I'll finish up talking about the density of states. So the density of states measures how many eigenvalues in a given interval. It's usually measured in one of two ways. Either a histogram of the eigenvalues called the density of states, or the integrated density of states, which is the counting function, this black function, how many eigenvalues less than a number e or lambda. And this says the first eigenvalue appears at about 0.3, and then there's another couple, and it jumps up by steps of 1 every time there's a new eigenvalue. And Weil's law, which is written here, it says the area in phase space less than a given energy level E divided by 2 pi to the power d gives you the number of eigenvalues less than E. So this is a quantity that you can calculate from the potential, and it gives you the green curve. And Weil's law says these things are asymptotic as E goes to infinity, which you can see here. But you can also see that they're not at all, it's not at all predictive for the first 100 eigenvalues or so, where there's quite a big difference between the green curve and the black curve. There it is with a blow up. So we had the following idea: replace V by W, our more effective potential. Now we should probably also replace zeta by something else, because we replaced Laplacian by L, but we didn't do that. We don't know how to do that. And we tried it. Love computers. And that's what you get. That's the Weil law computed with the effective potential instead of the true potential. And you see it's correct right down to the first eigenvalue and the second eigenvalue. It follows this curve. It wanders from it a little bit here, but it's much, much better. Even though Weil's law is entirely an asymptotic thing, this Weil's law seems to work down to level 0. So I think it's still, we still have to find out what you can do with this.
This was for all the, but that's for the continuous problem. The discrete problem can only capture a few.
So I've done my discretization well enough so that this black line is accurate for all the eigenfunctions. I computed the first several hundred eigenvalues.
Then that means there's a discrete Weil's law to be back.
Here there shouldn't be a difference between the discrete Viles law and the true Viles law,
Why not?
because I did the discretization to a high level. So I agree that it's not easy to get 160 eigenvalues correct, but you can do it if you take a fine enough measure and a high enough degree polynomial.
Or you use a very, very refined measure to compute it.
Or actually high degree polynomials on each interval.
Yeah, I guess what I'm trying to say is that this may be true even just do 160 asymptotically true. That's the kind of thing that I was trying to tell you the other day.
Well, we're going to hear a lot about this in the next talk, but we should also, you and I should talk about this in this context. But I mean, Jin-Chao's, this is a very subtle business because you have the true eigenvalues of the PDE, then you have the finite element method, and
I asked about discrete Laplacian, we are asking about precision of
For the Laplacian, you can prove the discrete Wiles law regardless of the accuracy, but you still get the asymptotics.
Well, you get asymptotic at infinity, this is precisely not an asymptotic.
And you get asymptotics without worrying about the accuracy. So namely, the Eigen values are about the same order.
Well, look at this, so the green line already gives you asymptotic, it's beyond the picture. So beyond the picture, everybody coincides.
But if I call it discrete Wiles law, is that you may not coincide to each other, but the asymptotic looks the same.
in this
Yes,
picture,
so the green line and the orange line and the black line, everybody coincides at infinity, and more precisely beyond this picture, but the point is that this is not asymptotic.
this picture has no discretization in it. The black line are the true eigenvalue counting function. The green line is the true Viles law.
What I'm saying is that if you use it's a 160 eigenvalue, right? If you only have the 160 kind of order matrix to compute the whole 160 eigenvalues for that matrix, you still have the same problem.
Well, okay, so that's something that you did. I wouldn't know how to do that.
Yeah, I mean, that's what.
But I didn't have a 160 matrix. I had a matrix that was like 160,000 by 160,000, and so I had no trouble getting 160 eigenvalues.
It needs to be easy to test whether what I said is correct or not.
Okay, so let's do it. Okay, let me finish off with the, well, here's a couple of more examples. So this is a Bernoulli potential in 1D, either 0 or 1. And what you see is the real Viles law makes two parabolas on their side as the shape, and that's not the right shape. The right shape is the black one. But the effective Viles law with W matches it quite well. Then here's the periodic case Christoph had asked about. That's a periodic potential. This is the corresponding effective potential. The true Viles law makes the same shape as here, and the reason is because the true Viles law is independent of rearrangement, so you can put all the black, all the ones to the left half, and all the twos to the right half. Or you can put them alternating, it doesn't matter, you get the same thing. That's why you get these two parabolas. But the effective Viles law depends very much. You obviously get a very, very different effective potential for these two cases, and it works in that case. And that's another one. And finally, the density of states. So density of states is something that people are interested in. There's a lot of interest in our group computing this Urbach tail, which is the rate of exponential takeoff of this tail here. And you can almost pick it up from this histogram, although you only got about 6, 8 eigenvalues down at the lowest levels. It's a little, would be nice to have it more refined. But this is a histogram with 8,000 eigenvalues. And to do that, I had to choose a random potential with 500,000 random numbers. So even though there's a 1D computation, this took 40 CPU hours to compute all these eigenvalues. And then I did it again with the minimums of W. That took 5 minutes. Gave me this picture. And you can see the difference between them. Qualitatively, it seems like you're getting the same Urbach tail, for example. So this is the direction we have to study a little more. It shows how promising this approach is, I think. And finally, some final observations. So of course, the main take-home message is that the landscape function or the effective potential. It's very easy to compute, but it really contains an astonishing amount of information about the spectra, at least for disordered Schrödinger operators and more generally as well. And it's a quantitative deterministic information. It's not information, it doesn't take as data the random class, Bernoulli or uniformly random or correlated of the potential. It takes as input data the exact realization of the potential, and it doesn't come back and tell you the expected value of the localization region or something like that. It comes back and says it's going to localize here and look like this. It's very deterministic information. The Eigen tool is a powerful tool. It's been a powerful tool theoretically for a long time, now using the effective potential, and maybe a powerful tool computationally as well. Combination with iterative algorithms, as we've already discussed, Rayleigh quotient iteration, adaptive mesh refinement, self-consistent iterations like Poisson-Schrödinger. And it's also clear that the theoretical story is a very complicated one. I have to say that we require rigorous validation to do good science. That's what I do it for a living. But it's not going to be easy to do here because the questions are very subtle. We need to clarify the limits of this approach, which equations it works for, how many eigenvalues it'll compute, how accurately, and so forth. So I think there's a lot to do, and we welcome help. Thank you.